Hello, I'm Amy Herfel, and today we're going to be looking at adiabatic flame temperatures of a system at a steady state. To begin, we're going to go ahead and draw our system. So for our system, we're going to be having some amount of air and fuel going in. In this case, our fuel is going to be methane, ethane, and propane, and we'll get to what that looks like later. And then on our side going out, we're going to have flame and hot gas at some temperature T. Just T out. All right. So the first thing we want to do when we're looking at this is look at the enthalpies and the masses, and we're going to make an equation for it. So we're going to say change in mass with respect to internal energy, make that better, times potential or plus potential energy plus kinetic energy. Changing that with respect to time is going to be equivalent to the change in mass times enthalpy plus potential energy plus kinetic energy minus, and that's going in minus, enthalpy plus potential energy plus kinetic energy going out. Sorry, I know I'm running off the board a little bit there, but the reason that's okay is because a lot of this equation doesn't actually matter. For example, since this is an adiabatic equation, all the potential and kinetic energies aren't changing within the system. And since there's no change, this side is just going to be equal to 0. And the same thing on the other side is the mass, this being a steady state equation, is also going to have no change. The amount going in is going to be equal to the amount going out. And therefore, the only thing we have changing is enthalpy. So we're going to have change in H. It's going to be equal to H in minus H out. And finally, if you would solve this equation, you would just see that the enthalpy in equals the enthalpy out. All right. So establishing that the enthalpy in equals the enthalpy out of the system, now we're going to incorporate temperature. So we're going to say that the heat of formation of our flame at some temperature T, which we have up here, it's T out, equals heat of formation of our flame at 298 Kelvin plus the integral from 298 to T of the specific heat capacity. Let me explain a little bit of this real quick, because most of the time, you can see that people don't integrate the specific heat capacity when you're using an equation. For example, if you're using it with water, usually it would just be multiplication. However, there is a huge difference between the heat of what's going in here and the heat of what's going out, causing us to need to integrate the specific heat capacity to accurately represent what we're doing. And so this is a difficult equation to find. So what we're going to do is we're just going to look on ChemCAD. It's equation 207, the giant database, or equation 107, my bad. ChemCAD equation 107 for this. And then we can look at that on the computer and see where to go from there. Okay, so now we're going to look up the equation for ChemCAD on ChemCAD 106. That's going to be equivalent to our specific heat capacity that we had on the board. ChemCAD equation 107. And then just to search through this, I'm going to do Control F, and I already have 107 in there. And that brings us to equation 107, which you can see here. So it's y equals a plus b times c divided t over the hyperbolic sine of c of t, or c divided t, to the second plus d times the same thing, except the c's are replaced with e's and sines replaced with cosine. Now, if you remember on the board, this value was integrated, which we do not want to do by hand. At least I don't, and I don't think anybody else does as well. So we're just going to look at this, and we're going to use computer software such as Wolfram Alpha to help us integrate this. The first part is a, which we can do in our head. It's going to, with respect to t, it's going to be a times t. And the second part is be a constant times all of this, which we can just go ahead and put into Wolfram Alpha. So what we're going to type is we're going to type integral integral of, let's see, C divided T, with that whole thing to be over hyperbolic sine of C divided T, with that whole thing to be to the second. There we are. And finally, we want to make sure it's with respect to T. So as you can see, the integral of this gives us C times the hyperbolic cotangent of C over T plus a constant. And the constant is, it doesn't matter too much in this. So that value will be multiplied by B here. And then we just have to do the same thing with this side of the equation, which the side of the equation is very similar. So it's just going to change all the C's from this to E's, and then the cosine or the sine is going to become a cosine. So we can go ahead and show that as well. So C to E and sine to cosine. Perfect. And it's all with respect to T as well. So that's going to give us negative E times the hyperbolic tangent of E over T. And now that we have this equation, we can go ahead and go back to the whiteboard real quick. Eventually, we're going to get to our coding, but first, I'm going to go through the fuel we're using and how you mass balance, or how you balance the fuel equations. Alrighty, now that we've looked at ChemCAD Equation 107, we're going to look at our fuel and what it's composed of going into this. As I said earlier, our fuel is going to be composed of methane, ethane, and propane. So we can go ahead and draw out the formulas for that. Methane is 1C, so it's going to be CH4. Ethane is 2, H6. And propane is 3 C's, H8. Alrighty. And that's our fuel going into the chamber. And we also have air. So for air, we're going to go ahead and add O2 for oxygen. That's what everybody thinks of when we think air. We need to breathe and live. However, one important fact that we need to pay attention to is that air is actually not completely comprised of oxygen. It's about 79% nitrogen and 21% oxygen. And therefore, we need to make sure we have nitrogen in this equation as well to account for going into our system. So 2. And since we're making flame and hot gas, this is a combustion equation. And therefore, when we do a combustion equation, your products are going to be CO2 water. In this case, since we have nitrogen, nitrogen will also be a product. So what we're going to do next is balance this equation. But before I go over that, I want to say why it's important that we account for nitrogen on both sides of this equation. Because when we balance it out, we'll realize that it's the same amount of nitrogen going in and going out, which is what it should be. But it really makes it look like the nitrogen doesn't change compared to the oxygen, which is becoming CO2 and water, and the carbons, which are changing places and all that. And that's because when you're putting nitrogen in, it starts at a very low temperature, just like the air and fuel. And it's coming out at a very hot temperature. And we'd have agreed that only so much enthalpy going in has to equal the enthalpy going out. And therefore, if nitrogen is taking up some of that temperature, our flame is not going to be as hot. However, if we didn't have the equation, the flame would be much hotter. And our goal in this is to try to find how hot we can get in an insulated box or chamber. So nitrogen is going to have a major effect on that. And let's say if you're out in industry and you want to make the flame at the end hotter, well, then maybe you'd say, all right, I need to find a way to eliminate this and only have pure oxygen going into my tank to result in a hotter flame. Anyhow, moving on to the mass balance of this. So I'm going to start out by looking at the carbons in each of these. So you have 1 carbon, 2 carbon, 3 carbon, and there's only 1 spot with carbons on the other side, which makes it really easy. So here, 1 and 1 match. Here you have 2, so we need to add 2 as well. And this one, we have 3, so I'll add 3 over here. Next, I'm going to move on to the hydrogens, because now that we've done that, there's also only 1 spot with hydrogens. I like to leave stuff that is in multiple places for last, such as the oxygen. It gets split up, which can make it difficult sometimes in mass balancing. So looking at the hydrogens, we have 4, and we only have 2 over here, so I'll add 2. We have 6 here, and 8 here. I'll do these at the same time, so we make sure we have 6 over here, so we'll have 3 or 2. To get 8 over there, we need 2 times 4. Perfect. So next we are going to look at the oxygens. This is the hard part. Now I am leaving N2 for last just because due to this equation, they do have some relationship with the oxygen, which I'll show in just a second. So for the oxygens, the first thing we're going to have, well, we have 1, 2, 3, 4 on this side. So we're going to go ahead and put a 2 over here. This 2 times 2 is going to be 4. These are all 2s. Can't read that. Then we're going to count the oxygens over here. So 2 times 2, 4, plus 3. So we're going to have 7. So 7. And we want to divide 2. It's 2 times 7 halves is going to be 7. And a lot of times in your mass balancing equations, you want whole numbers. So you have to multiply the whole equation by a common factor or something in order to get this to leave and everything else to be a whole number. But for this case, it doesn't really matter. So I'm just going to go ahead and leave it. Next, we're going to do our final oxygen, which is going to be, let's see, we have 6 plus 10. So 10 divided 2, 5. It's 5 times 2 equals 10. And now all that is left is the nitrogen. And the way you do the nitrogen, as I mentioned earlier, air is going to be comprised in this case of 79% nitrogen and 21% oxygen. So it's just going to be a ratio of whatever the oxygen is times that. So we're going to go, okay, so I have 2 oxygens, so it's going to be 2 times 79 over 21. I'm going to go down the line, do it for everything. 7 over 2, 79 over 21. 5 times 79 over 21. And same thing on the other side. Like I said, this part's really easy. We don't even have to think anymore. The nitrogen going in, equivalent to the nitrogen going out. Nitrogen's not moving, it's not doing anything except affecting our heat in this situation. So 2, 1. 5. Perfect. So now that you see our mass balance equation, what we're going to do is we're going to look at how we can put this whole problem into Python coding to make it easier and end up solving it. Alrighty, so now that we've done everything we need to on the whiteboard or the chalkboard, we're going to go ahead and look how to solve for the temperature of our flame in Python. So as you can see, I've already done some of the setup here. If you want to check back on the majority of it, you can look at my previous videos. I explained it pretty well in there. But the most important thing today is that we need to look at the data file. And as you can see, the data file that I've imported here just has a bunch of data on different molecules. And specifically, we can look at ethane. That's one we're going to be using today. You could look in here and it says it has the heat of formation. And we need to note that it has the heat of formation in kilojoules, or not kilojoules, kilomoles, not just moles, which will cause us later when we're solving this to need to divide by 1,000. Another thing is if you remember the equation 107 that we took the integral of using Wolfram Alpha, we had constants A, B, C, D, E, and so on in those, and we didn't know what those coefficients should be. However, if you look down here under our ideal heat capacity, you can see it has a whole list of coefficients, and that's what we're going to be pulling from for those. To start today, I'm going to go ahead and pull all the properties of everything I used in my equations, my chemical equations up there, including propane, methane, ethane. I'm just going to do E.props. So we'll start out with methane. That's the first type of fuel we use. Ethane. And what this is going to do is it's just going to collect all the properties for these in one place in this order. So then we'll do propane, oxygen, we have nitrogen, carbon dioxide. Finally, we have water. Perfect. We can do Shift Enter to make sure that runs, and I haven't made any spelling mistakes or anything. And it looks like it's all good. It has a green check mark, meaning it ran despite the little warning there. And we can go ahead and just do a little example of what that does. So we can call P.HFIG, which is the heat of formation of ideal gases here. If I just do Shift Enter and run this line, it's going to grab all the data points for methane, ethane, propane, and so on in that order. So here it is for methane, here's for ethane, and so on. So this line, if you're following along at home, this line is inconsequential to the rest of the code. It's just showing you what this does. Alrighty, so now the first thing I like to do is I like to begin by initializing my variables. Just think that's a good way to do it if you want to go back and change them later and make your program work for something else or different variables. So initialize variables. Alrighty, so the first thing I'm going to do is I'm going to initialize the fuel. So our fuel was methane, ethane, propane, said it a million times now, all composed of C's and H's, so fuel CH equals. And I'm going to go ahead and go, all right, so for methane, we have 1 C to 4 H's. And then for ethane, we have 2 C's to 6 H's. And then, big shocker, for ethane, we have 3 C's to 8 H's. You can go ahead and run that. And then we want to determine the moles of fuel that we're going to have. We're going to be putting in. So for this is just, for the sake of our problem, we'll say that they are 10, 1.5, and 1. So we do NP, we want this as an array. 10, 1.5, and 1. Alrighty. I got the right types of parentheses and brackets. That can always cause errors in your program. Alrighty, so now that we have that, we can go ahead and we can do the moles of C and the moles of H, moles of carbon and hydrogen. And they are just going to be equivalent to the matrix multiplication of the moles of fuel. Matrix multiplication, the @ sign, just so you know. Moles of fuel times the fuel. CH there. Alrighty. Now we can go on and do initialization for everything else that was in our combustion equations up there. So we have moles of CO2 are going to be equivalent to the moles of C. And we're going to have that our moles of, let's do H2O next. Are going to be equivalent to the moles of H divide 2. The moles of oxygen, oxygen are going to be equivalent to the moles of carbon plus moles of H2O there. And we're going to divide that by 2. Alrighty, and then finally, it seems complicated. I think this is the easiest. Did it so many times already. Moles of nitrogen is going to be equivalent to the same ratio it is always, 79 to 21%. Oxygen, because we have 79% nitrogen, 21% oxygen in our air. It's going to be multiplied by the moles of O, which we have already initialized. You can go ahead and run that, and it looks like it went really well. No errors in that code. So we can go ahead and move on. The next thing that we're going to do is we are going to do concatenation of some of the arrays in order to get our moles going in versus moles out. So I'm going to do moles feed for our variable for moles going in, and it's going to be np.concatenate. Choose concatenate, don't have to spell it that way. We're going to do moles of fuel, and np.array. We're going to want mole. So this is what's going in. So going in, we're going to have moles of oxygen, moles of nitrogen, and then we'll have our products here, but we're just going to put them in as 0. So next would come moles of CO2 maybe, but that's going to be 0, 0 because we don't have any CO2. These are the reactants. And we also have water, also 0, because as I said, these are the reactants. There we go. Let's see, we probably need some brackets here to make that run. Perfect. And we can do the same thing with the moles going out. So we'll call them mole product. Mole products. And mole products is going to be equal to MP dot concatenate. And this time we have used up all our fuel. So instead of having mole fuel, we're going to have NP dot 0 underscore like. We want it to be like mole fuel. So this way we're saying for us you can change the amount of mole fuel that you have, but you'll always have the same amount of zeros as mole fuel instead of just putting in ones or however many zeros we needed, which could cause problems if we ever need to change this program in the future. So I'm going to go ahead and just copy this part. It's a little similar to what we have, what we're doing right now. So I can go ahead and go. We have all that and we want to go. Okay, so now this is the products. So we have 0 oxygens. We've used them all up because we're assuming it's a complete combustion. Still we have moles nitrogen, but now also we have our products, which we have in as moles CO2, and then H2O, moles H2O. Okay, and let's see if we press Shift Enter here and see if it runs. Oop. Let's see. It looks like, you know what, we've forgotten this all needs brackets around it as well. So we're gonna go ahead and do a bracket there. H2O is not defined. Oh, that's because up here I did it as H20 instead of H2O. So we'll change it up here because I don't want to mess with having to remember to put H20s everywhere. And now it looks like this line works. So we can move on. And what we're going to do next is the code or the equation 107 we found in ChemCAD, and then we did the integration of that. We are going to go ahead and code that in. So we're going to go def delta HS, and we're going to pull in temperature, or T. And we're going to have it return that integrated code. So the first thing we had is, or the first thing I guess we need to recognize is that we're pulling the coefficients from the CHE thing, CHE tools, which I showed you earlier. What's it called? Yeah, all the big database. So we're going to have coefficient A here, and it's just going to be P.CPIGA. We need to multiply that by T because that's what we did when we integrated. A was the only constant that was alone. When you integrate that, you're going to get A times T if that's what we're integrating by. Alrighty, so then we're going to go P.C. Actually, I'm going to copy and paste this and just change the last letter for changing variables in order to make this run a lot smoother. So now we're going to have B times C, that's what our equation was, by NP dot tan H. It's going to be C divided T. And then we're going to want to subtract P. Oh, nope, we want to subtract the whole thing. So C, it's going to be D now, times same thing, but E multiplied by NP dot hyperbolic tangent. I want this to be the variable E divide T. Perfect. Let's make sure here that all runs. And we need to remember that, as I said earlier, we need to divide this by 1,000 because we had the kilomoles and we do not want that. So make sure everything runs. And it looks like that's good. There is a possibility that if I get the wrong end answer, while this all is, has correct syntax, I could have messed up and multiplied where I should have divided. So if that happens, we'll just have to go back and check, and we'll know if our answer doesn't really seem correct. All right, so the next thing I'm going to do is I'm going to do dev HIG. So we're going to do the we're going to be comparing our temperature that we have, which is 298 Kelvin, with the temperature that's going out. So we're going to go ahead and call in moles. Temperature. Water real quick. Okay, so what we want to do is we want to do the dot product. We're going to return the dot product of, so np dot dot G plus np dot dot delta. So we'll go ahead and copy and paste this. So what we're doing is this is the final heat. So we have the final heat is going to be equivalent to the heat of formation going at the start, or the final heat of formation is going to be equal to the heat of formation at the start plus the change in heat of formation. So here's the start right here, and now we're going to do the change in heat of formation. So we're going to do delta HS T, so minus the same thing at our specific temperature, 298 Kelvin. Perfect. So let's make sure that runs, and it looks good. So if we've messed up anything in there, same thing as the line before, just syntax, we'll have to go back. Syntax is correct, but we might have to go back and change something else. All right. So now that we've done that, all that we have left is we need to set up for our root solver. So we're going to go ahead and do an energy balance class, energy balance, and we're going to call in vector V, which is just going to be equivalent to temperature. Okay. We're going to return, if I can spell return correctly, HIG mole feed. So what's going in at 298 Kelvin, because that's our temperature of what's going in. We're going to subtract moles product, which is going out at some temperature T, and we're going to want to solve that temperature. Shift enter to make sure that runs. We're going to do our last step. We've set up for our root solver now. So we're going to do root of energy balance underscore BAL. We're going to put in our initial guess as 298 Kelvin, and just hopefully that will get us to what we need to. Otherwise, we can play around with it. And it looks like I have some mistakes. So you notice PHFIG is not defined. I believe it's because I need a, let's see. And it'll also, if you've done it right, when you're typing it in, it should come up like that as well, which will help you know that you've done it right up to that point. So I'll go ahead and rerun this. Oh, and see, you can see again, I've messed up some of the variable names and just calling in this because that needs to be a capital B. So we'll go on up and find it. Is that, and every time you change an error, you need to make sure you're pressing this play button to rerun and fix it. Otherwise, you're going to be like, I've changed it, but the class below it still thinks that it's wrong because it hasn't updated. So let's see. Mole product not defined. It's probably because I defined it with an S, didn't I? Yes. Okay, perfect. So after all that debugging, we get a pretty decent looking final answer. It should be pretty hot. We have our final heat is going to be equal to 2,717.31 and so on Kelvin. And I hope you've enjoyed this video and you've learned a lot from the deriving and just explaining of how we went through this process. Thank you so much.